ZK in 2024. I want to start with just like, I had a tech slide. I had sort of the latest research papers that came out, and on it I had Stir, I had Plonky 3, and I had Polymath. Was I missing anything?
Yeah. Circle Stark is a big one.
Okay.
Is this on?
Yeah, we can hear you.
Which is sort of the new generation of Starkware's like prover.
Yeah. In terms of that kind of research, though, where would you say we are at? Like, are we at a point where there's like breakthroughs coming? I felt like Binius last year was sort of like a really new way to deal with these systems. Or would you say 2024 is more of a year of like incremental adding on what we've already done? Like Stir, for example, is a breakthrough, but it's very based on Fry.
Yeah, they are breakthroughs, but they're also incremental.
Okay.
In a way that we've now understood, like, we know how to argue for these things. We know how to say, like, all right, I'm going to get a trace, commit to it. I'm going to run this vanishing argument, and I'm going to do these out-of-domain samples, right? It doesn't really matter what you do it on. And so far we've been doing it on, I guess, prime fields. Then we went to smaller prime fields, then went to tiny prime fields. Then we went to prime fields over a circle, or like a circle over a prime field. That's Circle Stark. But we're still doing the same thing. And we're still running Fry and Circle Stark. Stir is, I guess, a variant of Fry. And this is why I'm saying it's all incremental in that the big picture remains the same, but we're just plugging different components.
I see.
Or bringing in new mathematical objects like the towers or the circle.
Are there any, like this year, has there been any work that you feel like introduces actually a new technique that we haven't seen? And so just to give maybe a background of what I mean here in terms of techniques, like lookups are a technique that you'd see a lot of proving systems all of a sudden adopt. Folding is a technique that you've seen proving system being built around, and then others kind of trying to incorporate that technique. Yeah, is there a technique this year?
I have two answers. So the first, there's been a large trend to apply older techniques. So I think the SumCheck and the GKR protocols have had a resurgence of interest, which is really cool because they're actually very old. The SumCheck protocol goes back to the early 90s. GKR is from like 2008, which predates any of the snarks really on your slide, but they're being identified as really practically efficient, and I think that's a really cool trend and makes me somewhat optimistic about getting to a point where we can standardize just based on the Lindy effect.
Yeah.
My second answer is I'm very interested in the lattice fold work, and I think that's the best example that I can think of something that really is different and new that happened this year.
Is lattice fold a paper?
Lattice fold is a paper.
Maybe we should just discuss why is this different from what we've been doing so far?
Certainly. So as Nico said, like all of the Fry-based techniques come from sort of coding-based cryptography, or that's slightly different, but it's the idea of building snarks out of error-correcting codes and hash functions.
Instead of R1CS? No.
Oh, as opposed to elliptic curve code.
Oh, yes.
So
okay.
Broadly, you have snarks from elliptic curves and additively homomorphic groups, and then you have snarks from error-correcting codes and hash functions, and lattices are a different type of cryptography. What does that mean? It's based on a different computational assumption. It's about the hardness of solving certain problems in lattices, which are a different mathematical structure. And lattice-based cryptography is used for fully homomorphic encryption, and it's used in a lot of post-quantum signature schemes, but has not really found its way into the ZK world in terms of efficient schemes, maybe until recently. I think that's an ongoing trend.
Would say this trend takes off, what does it actually open up? Like, it sounds like if it's used in FHE, all of a sudden that FHE ZK overlap could be stronger. But does it do anything else?
I wish I could tell you.
Should I be asking a lattice?
It seems extremely plausible that you would have techniques that can bridge the gap between FHE and zero knowledge proofs better, but I need to educate myself more before I can make any
because that's the
claims.
only thing I know helps, but I wondered if
in terms of the unlock that you get. So all the elliptic curve stuff is great because our commitments are additive, right? I give you two commitments, you can add them together, and you have now a commitment to the addition of the things. With hash-based snarks, we have no homomorphism whatsoever. With lattice stuff, you're sort of in between. You have a bit of homomorphism, but not for too long. Like you can add a few things, but not too many. And so by going to lattices, you unlock a bit of the power of homomorphism, but you also keep sort of the post-quantum thing that you get from not having a group.
Nice.
So yeah, you're sort of in this in-between realm.
That's a good one though, the lattice-based snarks. Is there anything else that we could think of that happened maybe? I mean, we're only, 8 months into the year.
Yeah.
Like I mentioned polymath, but I actually don't know polymath. What's it doing?
That's really interesting, actually. It's so all the sumcheck GKR work, we're back into it because we wanted very efficient provers. And Groth 16 has been such a standard because it's sort of the smallest proof we knew. And now these works, polymath, and there's a recent work like I think it's called Gerudo and Parry, which are also like smaller snarks than Groth 16. Like that's why these are cool. They go back to the trusted setup per circuit model. They go back to pairings.
Okay.
And they add in random oracles. So they add in this sort of interaction part. And now you get even smaller proofs.
But trusted setups are back.
Yeah, you're back to trusted per circuit trusted setup.
Yikes.
So this is more of a cool theoretical thing. If people are okay with their trusted setup for Groth, maybe they're okay with doing this and posting it on chain. I don't know.
I mean,
narrative to be developed.
Also, I mean, trusted setups in general have also been developed, so they're like a little easier to run. There's a lot more.
I've heard marketing teams that want them.
Really?
Yeah, because it gets communities involved. It's like, hey, join our trusted setup, and people hope they're going to get an airdrop, and
interesting. Okay, so polymath seems more like going back to earlier work, making an improvement. Do you see a path where that gets incorporated? Like, I don't know if this is impossible, but like into the things that came after Groth 16, the things that started to remove the trusted setup. Could it down the line be used in that?
I'm not sure. It's probably more going to be used as, like we use Groth 16 today, as like this final layer of recursion to get a tiny proof.
Interesting. It's funny, like after making that presentation, I realized I sort of want to format it again a different way. Like maybe I'd do it both ways. I'd show the, narrative year by year, but then I want to show like this work led to this work, because I've never seen that myself. And as I was putting together this history, I was like, oh man, you can really see it tracing. Certain researchers also like writing subsequent papers, and then I love it when it's like an older thing comes back into the fray. I didn't quite show that, I think, in my slides, but I want to try to do it.
There's two funny things. One, there's this saying that every idea in ZK comes from a Groth paper from back when, which is pretty true.
And
the other one is
maybe, or Dan Bonnet.
Also,
one of those three, probably.
For a while, like
it was all Jens
the only guy into this.
Funny.
The other thing is this old like Bayer Groth paper that doesn't see much. It's just like, how do we prove a shuffle, right? And it has little building blocks in it. Turns out one building block then became the permutation argument of Plonk.
Okay.
And the other one became what we know as bullet proofs.
Oh, wow.
Like, there's super fun like history and lineage that you can find through these papers.
That's so nice. I wonder if we could continue to talk about research if you have anything else on 2024, but if maybe I'll leave it.
Maybe Jim?
I think I've mentioned the things that are most exciting to me.
Cool. Yeah. In that case, I want to talk about the tech that came before, and if we think so past tech narratives, I sort of mentioned these, some of these like techniques.
Actually, sorry.
Oh, you have one?
Are you counting all the sort of Jolt stuff as last year?
Yeah, okay. But we could, but actually, I mean, they implemented it this year, right?
Yeah, because that is super cool. That's also a paradigm shift from the
sumcheck stuff.
Not only that, but also the let's do everything and then look up. Like that's quite a big difference between like, hey, can I have constraints? How do I express risk0 risk5 as efficiently as possible? And they went in and said, hey, we're just going to make a table and you're going to check if it worked or not.
Yeah. So actually that was the next thing I was going to talk about, was like those threads or techniques that we've seen getting better and better and better. Things like lookups, folding, and small field work, which I know you're really focused on. But I'm kind of curious, like, are any of these also hitting like dead ends? Like, are they coming a little into conflict with one another? Like a question I had wanted to ask you at the end of your talk, but also felt like a bit of a dumb one because I think I know the answer, but it's like, can you use folding? Can you use lookups in these small field systems?
Right. There is some conflict there.
Yeah.
So folding, you need some sort, well, for like Nova style full folding, you need homomorphic commitment schemes, and typically we're using elliptic curves for that. And so elliptic curves cannot use small field techniques. Your elliptic curve base prime or your base field needs to be big enough for the same reason that hash outputs need to have a certain size. Lookups, I think all of the lookup constructions I can think of, except for the sort of CQ line of work, do work for, Binius and small field Starks and so on.
But not CQ.
Not CQ.
So that means not Calc, not Alu.
All the works that are sort of at runtime independent of the table are pairing only.
Is this because, like, what's the characteristic of these lookups?
The Calc and CQ line of work make use of basically the algebraic structure of KZG commitments.
Yeah, okay, that's why. And it's not KZG.
Yeah, it's not.
You can't
KZG.
do that.
In fact, it's not even, you can't even use those with bulletproof style elliptic curve schemes.
Actually, we haven't even plugged. Jim is one of the authors of Calc Plus.
Oh, are you? I didn't know that. So you know.
Yeah.
I'm
well
can't
aware.
be used. Wow. On the folding side, I mean, so folding, you're saying absolutely cannot.
So there is a work on accumulation without homomorphisms. There's sort of some bounded amount of, basically, okay, in terms of lineage, you have full proof recursion, which is when one proof fully verifies another proof, and then you had accumulation, which is like the halo work, and then you had folding, which is like even a refinement of that. And so there's some work on accumulation without homomorphic commitments, but there are some limitations to that. It's not sort of full folding.
But it's still accumulation. It's not just recursion. Because I always find there's sort of like a slight...
Yeah, there is some savings that you are able to capture even without homomorphic commitments, but without doing full proof recursion up to some sort of bounded amount of accumulation.
Cool.
Yeah. And back to the earlier point, this is where lattices are interesting because they give you that sort of ability to fold things, but you don't have all these weird like cycles of curves that you need. Like, yeah, it's an in-between.
Nice. So moving a little away from the tech narrative research side, more towards these, I didn't know how to say it in the presentation, like topics, use cases, like uses, like infrastructure pieces. I don't really know what they're called. It's basically, I'm trying to look for like a meta word for the coprocessor, ZKVM, like the tools, the prover network, like infrastructure pieces, ZK infrastructure pieces. Anyway, that's what I want to talk about now. I still have to find what that meta term really is. But I feel that since, like, at least the way I've thought about this is like scaling compression was sort of on the infrastructure side. It wasn't about the end user's privacy. It was just about like a computer system, a distributed system having new features. After like in 2023 to this year, I feel like there's just been this, like every few months, sort of a new narrative occurring there. So I believe coprocessor, I think I first heard about it beginning of 2023. I don't even know if the term was coined, but that was what was being described. This idea that you could like take some external data and prove it with ZKPs on chain. So it's like replacing an oracle in a way. And then we had the ZK-VMs that went beyond like before I always thought like ZK-EVM, then ZK-VM, but then ZK-VMs they had this uniqueness, the fact that you could like put not some custom ZK system under there, but like Rust within it. And then most recently we have this ZK supply chain. And I'm just curious, like maybe, first of all, am I missing any of those narratives? And I think we should kind of talk about these pieces, because what I also find is that they're merging into each other. Like the coprocessor teams also often have a prover network proposed. So, or the ZKVM will launch a coprocessor. Like it's sort of like the teams keep moving around. So for me to classify them becomes more and more complicated. That's why I'm trying to come up with a meta term for what these are.
I think we won't, because some of these things are products.
Yeah.
Some of these things are networks, and some of them are just mental models. Like the coprocessor is just a mental model for how can I use a zero knowledge proof? Well, I can use it in a way that I do some work and I prove on chain that I did the work. Like it's just to help people to think about these things. It's not a specific product. Like any ZKVM is a coprocessor.
Okay.
Any zero knowledge proof is a coprocessor.
But then you have specialized coprocessors, I guess, where they are building out the entire flow of info. Like for example, if they want like historic chain data, they will build like there's.
So I'm going to write a circuit that's very good at historic chain data.
Yeah.
And I'm going to give you sort of an SDK for you to write applications that use this. And I'm going to call it a coprocessor. But at the end of the day, tech-wise, we're still building the same thing.
Wow. So are coprocessors ZKVMs? Or vice versa?
The easiest way to build a coprocessor that can coprocess anything is to build a ZKVM,
I mean, the way I would look at it, I'm not sure there's a single unifying thread, but I think that ZKVMs are one of the two. I would say that ZKVMs and proof recursion are the two biggest unlocks that have happened in the last 5 years. Why? Well, with respect to VMs, we can look at just the history of computing. Like back in the 60s, you made custom digital circuits for all the things you wanted to do. And then there was this idea that I could build a universal circuit. That's what we call a CPU now. It's a single digital circuit that takes in a program, and by feeding it this additional input, which is a program, I can make it do anything I want without writing a new circuit. And it was so successful that we don't even think about circuits. We think about computers now. So that's why I think VMs are so powerful. It unlocks that programming model that we're used to for ZK, if you're willing to eat some overhead or in terms of the computation. As far as coprocessors, I think the thing that succinct proofs really let you do, I think of it as you can extend chains of trust. So you need some root of trust somewhere. In the case of a coprocessor, if you're trying to prove statements about historical Ethereum blocks, then actually Ethereum is my root of trust, but I'm extending the capabilities of that to prove some new claims about that historical data. Or in the case of any other type of oracle or zk-TLS, or you gave the example of image provenance, then I have this camera that's signing an image. That's my root of trust. But then I can extend it to make additional claims about the image. I can claim that these filters were applied, or I can prove some private property about the image that I don't want to reveal. So it's this really flexible model where we can extend, roots of trust.
And sort of to go back to your example though, I think maybe originally, or even when the concepts around these things first came out, people would then go and try to build that single case. Like this, so I want this data and I want it to do this thing. I don't know if coprocessors were that, but you'd have to build just that piece. But what you're saying is with the ZKVMs, there's now a general purpose place where you can do all of that stuff in a faster, easier way. So you're not individually designing a circuit for that particular case.
Exactly. And you're able to use the programming tools that, not only the programming tools that we're used to, like Rust or C++, but the programming model that we're used to.
It's funny, with ZKVMs, I also always put them in the category of ZKEVMs. It was sort of like ZKEVM, then ZKVM. They look similar, and they're similar.
There's a good reason for that, yeah.
And yet the ZKVM, I guess ZKEVMs, they let you use the EVM in a general purpose way. But why is it that this concept of verifiable compute is not there, but rather with the ZKVMs?
Do you want to go?
Yeah,
first?
may I have my hot take is blockchains are platforms for verifiable computing on shared data
all the time.
That is almost definition.
They've always been, right? That's what a smart contract is.
Yeah, and so the EVM is some sort of virtual machine that was designed from day one for verifiable computing. It's just that we weren't doing cryptographic verifiable computing with succinct proofs and snarks. We were doing verifiable computing in that all of the
With
full
consensus.
nodes were going with consensus. That all the full
with the
nodes
economic
were gonna
game,
Yeah.
not with the with a mix.
But also with duplication of the work. Like everyone did the same work, and that's how we verified it. It's because we trusted all these
Yeah.
people to run the same thing.
So in that sense, it's sort of a natural fit that you're going to take the verifiable computing platform that we're used to, and then you're going to try to produce succinct proofs for it.
I think the verifiable compute narrative within the ZK space comes from people fighting back against, hey, ZK means zero knowledge, it means privacy. And therefore teams have come up with a new way to say like, hey, we're doing ZK without using ZK because they're not doing privacy.
Yeah.
So they said we're doing verifiable compute.
Interesting.
Just like a lot of rollups are now like validity rollups or integrity proofs rather than ZK proofs.
Let's talk about the other pieces of this group of ZK infrastructure. I don't know what to call them.
Yeah.
The ZK supply chain. This is it's a term that, for me at least, it was pioneered by Shumo from Nebra. It's the first time I saw that laid out. And so the idea there is you have these ZK VMs, these coprocessors that are creating lots of proofs. I mean, roll-ups would fall under that as well, potentially. And now you have all these proofs, but who's making the proofs? Who's actually doing the proofs? Is it the network itself? Or is there like a server,
AWS.
single server somewhere? And then there's this proposal to potentially decentralize the provers. It's an untested ground. Like it's an interesting concept, but I think there's a lot of people who aren't sure if that will actually become a marketplace the way it's understood, or if the networks like the ZKEV or the roll-up teams, if they're actually going to want to have someone else doing their proofs at all. Mm-hmm. But and then there's this other side, which I was struggling with the name of, verification aggregators, proof verification aggregators is I think what they're going as. And here, I don't fully understand what that is yet. So as I understand, it's like, what I do get is it's like someone's creating the proofs, and then someone has to aggregate the proofs to make it more efficient when you put it on chain. Is this correct?
That's exactly it.
That's what it is. And so there's these two potential marketplaces, maybe, in the proof creation, which is what I think is the ZK supply chain.
Yeah.
And to add one more point about why the aggregation is important, it's because there is a fixed proof submission cost to verify a proof on an L1. That's like you end up with a constant size proof for as much stuff as you wanted to jam into a single proof, and you need to pay this fixed cost to put it on chain. And so it makes sense to have some
batching.
That's
what that is.
Yeah.
But is that but then there's a marketplace for it, or would it just be like an individual agent that just like a single I guess it's to avoid the centralization part, that you don't want one central agent just batching?
Yeah, I'm not sure, frankly, if there's like a majorly successful one that's like out there right now. It's sort of within each rollup ecosystem that each rollup is taking all of the transactions for their network and posting a single proof on chain periodically. But the more you can sort of aggregate those together, the more frequently you're able to post updates and get the L1 verification kind of stamp for everything that goes into that batch.
Cool.
There is a trade-off, by the way, which is, yes, we're going to aggregate a bunch of proofs and it's going to be cheaper to put onto chain, but we now have latency because I'm going to submit my proof and I'm going to have to wait for other people to submit theirs and then go onto chain. So all these things of like fast finality, all this stuff, like starts going a bit bonkers because transactions are now sort of floating. You don't know who's going to be proven before who and who's going to make it to chain before who.
Oh, wow. Does that become like an MEV?
Well, it's hard to see what's
aggregation
inside
MEV
the
issue.
proven transactions.
Yeah.
Like if you have a proof that's a batch of 1,000 transactions, you're not really going to see what's in it. But yeah, there might be some
weird
price reordering happening.
Strange. I don't know. Do you have anything else to share on that? I'm kind of curious what your opinion is on it. Do you think it's viable?
I think it's viable for things like rollups that do want to be decentralized. They're going to need to incentivize people to make the proofs on the prover market. side. I think there will also be incentives to pay less to put your proofs on chain. So you will be willing to pay this aggregation service. Whether or not these things are lucrative, I don't know. And then there's this whole other thing, which is you lose privacy.
Yeah.
Right? Like in this whole delegation thing, there's no privacy. So if you're interested in privacy, we either need to look at privacy preserving delegation, and there are protocols for this, or we're back to like proving on the client.
Mm-hmm.
I think a lot of this stuff is useful, but at the same time, I think there's a tendency in the blockchain space to build infrastructure for the sake of building infrastructure. And it's to, think, oh, well, we need a new protocol layer for this on top of this protocol layer for this. And I think that we should have the gut reaction of making sure that all of that is actually serving some purpose. And the thing that I kind of consistently hear is that the thing holding back ZK adoption is performance and usability more so than the lack of a proving network or decentralization of proving or insufficient aggregation. So
I mean,
wait, can the verification layer argument be pushed forever of hey, wait, I won't post it on chain just yet, let me aggregate it once more. Just one more, please, man.
Yeah. But going to that issue of, so I hinted at this in the slide on kind of challenges, which was funding and where it goes. And I recently, in the last 3 months, I encountered a team that was going to be doing something very app focused, very kind of closer to the user, a use case that was really interesting. And they were having a super hard time fundraising. Usually ZK projects in the last 2 years have had a pretty easy time. This was a team that was not infra. Mm-hmm. They were not pretending to be infra. They didn't, partly it's they didn't have a token plan.
They were just too honest.
But they're true but they're also they're the thing that all of these general purpose application they need, the general purpose VMs need applications to be built on them, and those need to be popular. And here was one, maybe it would or would not have been popular, but it's just the challenge they got, or just the resistance they felt from the funding side of things was a little worrisome for me, because I was trying to help them too. I was trying to sort of introduce them, and I just saw them get no after no after no from VCs who have done riskier deals than this for larger amounts, and they should have the risk appetite, and yet they're wary. And this was a bit of a concern. I don't know if you've seen anything like this, or if you are aware of or if you meet with app teams, or maybe there are no app teams and this is the only one. I don't know.
That's definitely concerning. I'm all for people actually building applications with all the infrastructure. I can't speak to that example, but I do think that maybe until recently, we were in a world where if you wanted to do anything meaningful with ZK, it was a lot of work, and you were going to have to hire a cryptographer or something. And that also doesn't make sense, that in order to build your application, you would need some extremely specialized knowledge and potentially build a new proof system. And
for sure,
none of that made sense. And I think we're the state of the art is improving in terms of people being able to build useful stuff with reasonable performance using tools that are not that hard to use with a meaningful level of security. So hopefully that is the unlock that's needed to.
Are you saying ZK VMs are stealing our jobs? But no, for the application thing, I think if you're a sort of classic investor, you're are they building tech? If they're not, that sounds risky. Then if you're a tokeny investor, hey, do you guys have a token? If they don't, no. So you end up with teams having the knowledge to use all these tools or even develop their own, not knowing exactly what application is going to work, not having people backing them for a specific application. And so you end up with brilliant design studios. And you have teams like Cursive, which I think are amazing. Yeah. They come up with these really cool MPC protocols that people have been using at these conferences essentially. But yeah, I think for me, they fall in that category of incredible know-how, super creative, but probably it's hard for them to raise on a single application.
I actually, as we talk about that, I think back to 0x Park, and when they started, they were full of just ideas, use case ideas. Like you could do ZK for this, you could do ZK for gaming, you could do ZK for this. And they went through a phase where they also had to, because of the state of the tech and tools, they ended up kind of being like, okay, we have these great ideas, but man, we're going to have to work on all of this. And you could see them sort of shift focus in terms of the workshops they were hosting and projects that they helped get funding and sort of incubated. They all kind of turned to, okay, actually, we need to build more of the tools. Maybe we're now back at the point where we could have a studio like you just described, doing more on the use case front, which I hope happens. I mean, this is why we host these hackathons.
Yeah. I mean, ZK email came out of this sort of energy, right? And like Ayush went and wrote the research to have these ZK nullifiers, and then he went and built his ZK email. Yeah. Which is amazing. And you do have like TLS, no, sorry, which one? ZK P2P, like built on top of ZK email. Like that is an application. I don't know if they've raised or how they're doing. I think that is one application that I see alive and like.
I don't know who did ZK TLS. Is that?
So ZK TLS is a whole category of like.
But wasn't
papers and
there's
applications.
An initial implementation that a lot of people are now like.
Yeah. So the initial implementation was called TLS Notary.
Oh yeah.
And the initial paper is called Deco.
Yes. Okay.
Yeah, MPC TLS I find is a better name for it.
Really?
Because, like I was saying in the talk, you do have this verifier that is online all the time, that is interacting all the time. So it's much less this non-interactive, publicly verifiable ZK stuff. It's more of a MPC. You still have zero knowledge, you still have privacy, but I want to capture this really interactive setting.
Nice. So I wonder, maybe we can open it up for one question from the audience. I think I'm getting pulled off the stage. It's also quite warm in here. Thanks for sticking with us. But yeah, is there any questions or anything about what we've talked about that you want to expand on? And if not, we have one.
Hey, I was wondering, what do you guys think about the security for the ZK tech that we have, the ZK infrastructure? Is it all good tech?
It's a really good question, Anna.
I think that's a great question to be asking. No, I mean, these are very complex systems, and it's going to take a while before you should really trust any single one of them. I can say a couple of things that make me somewhat optimistic about where we could possibly end up with the security story. For verifiable computing, for snarks, not zero knowledge, there's a pretty amazing thing that's true here, which is you only need to audit the verifier for security. The prover kind of can behave arbitrarily, and it won't be a security risk by construction. So that's
if
cool.
The papers are correct.
Sure, you need to, like you need to audit the research and the verifier implementation. Yep. When you deal with zero knowledge proofs, a bad prover could potentially leak private information. And then the second thing is that you can compose, proof systems. So if you were to only accept a claim if it was proven by multiple proof systems, then you could get more assurance that way and sort of hedge your risks. But of course, that means more work to go and implement several proof systems that are all, able to performantly prove some statement.
Yeah. I think we're still far from like sturdy, battle-tested protocols. Like having done a bit of auditing with geometry research, like we've seen how hard it is to audit these things and to really make sure you didn't miss anything. All the audits I've been finding online have a lot of like severe vulnerabilities or like critical vulnerabilities, and it's great that that they are published. But I think we shouldn't also like have an audit report that says here are these 5 severe vulnerabilities that we fixed, and here's my version 1.0. Like no, I think if you had a bunch of severe vulnerabilities, like review the circuit, audit it again until you get a clean audit, right? But yeah, kudos to the teams that do publish these reports with big vulnerabilities, because it's very important for everyone to know about these things, for the community to learn in general. And I'm kind of worried that there's a lot of audits that are done and never published because they're so like damning. And then there's the whole like security levels and making sure parameters meet the right levels of security, and what conjectures we're making about the objects we're using. And yeah, some will argue that roll-up teams have been very liberal with these. Yeah, you seem to,
I feel like
not like it either.
ZK security may deserve a panel of its own one day
Yeah,
somewhere.
yeah. I mean, there is work going into it, right? Like
Yeah.
there's a taxonomy of ZK vulnerabilities or like
Sure.
circuit mistakes that you can make that came out recently.
Totally.
Yeah,
Cool.
get into auditing. There's a lot of work.
There's a lot of work. All right. Thank you guys for this panel.
Thank you.
Thank you all for sticking with us for the ZK kind of afternoon here. I just want to share one thing. We've been sharing these booklets around. This is the State of ZK report from the ZKV team. We produce these every quarter. They're just like a little look at what's been happening, the map of ZK, latest research. So we're going to be leaving them around. I think we had 70. I doubt we have 70 now, but if you're interested in these, please grab one. Yeah, and thank you guys.